Right, another video on mechanisms, this time just the two of them, which have got electrophilic at the start of their name. I don't think they're very closely related really. Obviously there's something in their name, but all these mechanisms involve an electron pair donor bonding to something electron deficient. I'm going to use skeletal formulae for this demonstration. I'd advise you to not use skeletal in your actual exam, but rather expand it out, show the double bonds, just make it completely unambiguous what's bonded to what. The danger with skeletal is you just put too many carbons in by just extending the chain by one. Now, I won't spend too long on this one. It gives us a chance to talk about the major-minor product split, which sometimes arises, and we'll in this one here. Just as a reminder, there are three electrophiles on the spec for electrophilic addition. It's either hydrogen halide or bromine or sulfuric acid. Sulfuric acid there is conc sulfuric acid, hence it actually having its hydrogens intact. I know I've said this a few times over the years, and hopefully when I say it now you'll remember it, but the point is it's conc acid. There isn't enough water for this strong acid to fully ionize because it's not in solution, it's like it's pure liquid form or close to it. And so actually the majority of the sulfuric acid molecules present in conc H2SO4 have actually got their H pluses attached, i.e. they haven't ionized, even though it's a strong acid which fully ionizes, because it can't, it's got nowhere to go. Anyway, more on that later maybe. So either way, you get this first step where a delta plus atom bonds, has a bond formed to it basically by the electron-rich CC double bond. Again, similar to what you may have already heard in the nucleophilic video, there's always a delta plus atom, okay? First of all, if it's sulfuric acid, it's simply the H because it's bonded to something a bit more electronegative than itself. In the case of bromine, there are obviously two of the same atom, so there's no permanent dipole across that bond. But when the electron cloud of the Br2 molecule gets close to this electron-rich CC double bond, there's an induced dipole. It's along the lines of van der Waals forces, but it's not actually just intermolecular forces we're talking about. It induces a dipole, which then means the bromine atom, which is nearer to the double bond, becomes delta plus, electron deficient in other words, and so the electron-rich double bond bonds to it. Anyway, I haven't really left myself enough space for this mechanism now. I've talked about all that. Now you know that there are two possible products here. You either get a primary or a secondary carbocation from propene. Obviously watch out, it could be a primary and a tertiary if there's like a branch in there, so just look at what it is. These both happen. Either way there's a C+, which is about to have a bromide or a hydrogen sulfate ion bond to it. And the question will direct you if you want the major or the minor product, and then it might ask you for why. So I'm going to just quickly restart that because I've made a real mess on the page, albeit there's nothing wrong that you might have seen then. So let's get this done pretty quickly now. So here it is in not skeletal form. There's HBr. Bonds to that. No, you don't need to show the partial charges. If you do, they have to be right. If they're wrong, you lose the first arrow mark. So get them right or just don't show them, okay? I'm going to go for the major product forming intermediate, which means I'm putting a secondary carbocation down there. So this CH2 group on the end has gained that H and becomes CH3. There's the intermediate. Then along comes the bromide ion. You need the lone pair on it, so an arrow can go from it to the C+. And there we are. We've got two bromopropane. Easy peasy. I'm not going to waffle on now, but the reason why this is the major product, the classic mistake that students make is they start saying, yeah, because this product is more stable than the one bromo alternative. That's nonsense. It's just not right. Yeah, this is the major product. It is formed in greater abundance. It's nothing to do with the product's own stability. It's to do with the stability of this intermediate. Carbocations are inherently unstable. They happen all the time. They're not like, impossible, but they're like a hurdle, like an energetic hurdle to get over. And the C+ being placed on the second carbon here just makes it more stable. And again, check your notes on why. We've talked about it at length back in year 12. It's because there's a greater inductive effect when there's two alkyl groups on that C than when there's only one, okay? So it's the carbocation intermediate stability, which leads to more of a given product. The products themselves have very similar stabilities. It's the way that you get there. It's the middle road, and so on. Now that's electrophilic addition. Our definition for a nucleophile is an electron pair donor. Our definition for an electrophile then is an electron pair acceptor. So in this case here, the nucleophile is the alkene. Okay, with this electron-rich CC double bond, it donates half of its double bond, i.e. one of its two pairs there. The electrophile, in this case, is delta plus. It's just simply the HBr molecule, but strictly speaking, it's the delta plus H. So I've put E plus there. It's not a whole positive charge. Every mechanism, whatever its name starts with, involves a nucleophile bonding to an electrophile. And it's just for some reason, some are called electrophilic this and others are called nucleophilic that. Anyway, it's not very closely related, but now we've got electrophilic substitution as well. This is the benzene reaction. So there are two electrophiles that we need to know about, aren't there? There's the nitro group, and then there's the acylium ion. Just a quick bit, because we want as much detail as we can here. I'm not going to go through the equations that show the generation of these now. That's all on the spec. It's in your notes, and you do need to memorise the equations for forming NO2+. It involves conc nitric and conc sulfuric acids reacting together. There's an equation that shows a bunch of products, including NO2+. And for the acylium ion, I'll write that one down, that word, acylium. There it is, in case that helps. It's an acyl chloride with aluminium chloride. So you've just got to know that stuff and write equations for it. The focus of this video is the mechanisms. So I'm going to work with nitro. The first arrow has to come from the circle, which, remember, represents the delocalized electron system in benzene, to the positively charged atom, which is the N in NO2+, and the carbonyls carbon in COR, whatever R is. Okay, that gives us that horseshoe intermediate. Now, again, if the question had specified a particular product, maybe stuck a methyl group there, and told us we want the nitro group next to it or something like that, then we better just be cautious to honour that, basically. Just make sure that you're matching the question. It's fine if it's benzene. So imagine that the question wants us to put a nitro group next to the methyl. So I need to show that it's attached. I need to expand out the hydrogen, which is also on that carbon, because that carbon hydrogen bond's about to break, because it's substitution. The NO2 replaces that H. The horseshoe visits the other 5 carbons, remember? So that's perfectly good. It's clearly just not visiting that one. And yeah, positive charge in the centre of the ring. So a mark for that arrow, a mark for the intermediate, and then a mark for showing the CH bond breaking. So that's an arrow from the bond going into the ring. Send it to the plus, which you've put at the centre of the ring, and you're good, okay? That gives us the products. Just imagine that that was the product they wanted. I've got it correct with the NO2 where the question told me to put it, which is next to this methyl I've just conjured up out of nowhere. Fantastic, there it is, okay? Alternatively, again, if that had been the acylium ion, then you can imagine the arrow just goes to the C+. That's C, carbonyl R there, and you'd end up with just this product instead. Or whatever it was that's relevant to the context of the question. You make a ketone in that case, okay? So there's not much in common really. Part of the thing, some of the things that sort of come off the side of this though. So we say it's a classic, isn't it? Alkenes undergo addition reactions. The mechanism they follow that we study is electrophilic addition. There are also addition polymers that don't go by this mechanism, and we don't have a mechanism for it. There's hydrogenation, where you use a nickel catalyst to just add H2. Again, as far as I understand, it doesn't go via this mechanism. But whatever it is, it's an addition reaction. The double bond gets replaced by a single bond, doesn't it? Whereas here, we've got this whole benzene stability consideration. If benzene underwent addition reactions, if it acted like an alkene, we know that it's not an alkene despite some sort of surface level similarities. If it were to undergo addition, then we'd end up losing some of these delocalized electrons, and that would ultimately take away that delocalization, which confers stability to the molecule. So if it went underwent addition, you'd take out some of these delocalized electrons, they'd be committed to bonding instead, and you wouldn't have as much delocalization of electrons, so it would be less stable. Nature doesn't like that, which is why it doesn't happen. Anyway, I hope that's been helpful again. There we go.